Okay, here's a little bit of detail that's very relevant to any kind of analyses or modeling where you're going to be using multiple different rasters. You need them to be similarly cell-sized and concurrent, meaning the cells need to line up with one another. Yes, we can just bumble through our analyses and not think about things like this, but the results are neither repeatable or are they necessarily defendable if you don't know what you're actually comparing cell to cell. Okay, so for the setup here, what I've got is a small LiDAR tile. It's half-meter LiDAR covering Monroe Mountain in southern Utah. And then I've got AC stands for the autocorrelated photogrammetry data from the mapping portal, Utah mapping portal. Cell size is 5 meters, and that's this larger cell or larger data set that you can see here. The extents of these are obviously going to be different because raster tiles tend to be sized by their overall file size, and because LiDAR contains so much more information because the cells are so much smaller, the downloadable files are much smaller in extent, but same overall file size, just different spatial extents. Okay, so because it's half-meter data, we have a very small area that we're going to be comparing. You might enjoy pulling a couple of different, 2 to 4 LiDAR tiles and mosaicing them together so you have more area to work with to find interesting comparisons. But for us, this is where we're going to start. Let's look at the values here really quick. Our smaller data set has a max of 3,423 meters. I'm rounding. And that's fairly close to what our autocorrelated DEM is. It has a max value of 3422. And so one question is, we're looking at an area that contains a peak. This is for Monroe Mountain. And so we would expect that peak value to be very similar. Why do you think the autocorrelated peak value is slightly lower than the LiDAR? I don't know this for sure, but my intuition tells me that because it's a 5-meter cell, peak value is going to take in areas around the peak that are a little bit lower, and they're going to bring that average down. Now, some raster data sets actually use the surveyed value and preserve that as the peak value. Some are interpolated, and so you do get a little bit of rounding that comes from averaging the surrounding values. Worked with 5-kilometer DEMs and looked at peak values, and you can imagine that if you use a surveyed peak value, it's going to be very different to interpolate from there over a 5-kilometer area down to the next nearest cell. So it gets a little bit tricky. But that's that. Let's look at our low values. They're about 1,000 meters apart. And why is that? Well, it's because the bigger data set goes all the way out to the valley, and of course it's going to include values that are quite a bit lower than the smaller tile. So these are things that you should be noticing when you bring data into your maps. You should be kind of subconsciously taking all of this in and asking yourself if the values make sense. Are they logical? Do they make sense with the physical world that they're representing? And things like that. Okay, so let's get into the resampling. The reason that we're going to resample the 5-meter cell sizes down to a 1/2 meter cell size is because we want to make sure we're preserving all of the detail in our LiDAR data set. We want to be able to make a cell-by-cell comparison between the two, and if we were to resample the smaller cells up to the bigger ones, we'd probably be averaging, or we could take a max or a min value, but we're going to be losing a whole lot of information. So there's absolutely nothing wrong with taking a 5-meter cell and breaking it into 25 equal cells. But that gives us a one-to-one comparison for all the information that's going to be happening for those same 25 cells in our smaller cell size data set. All right, so let's go into resampling, and I'll show you some of the tricks here. Oh, and also, both of these data sets, resampling, have been projected. We're not working with units of degrees and, funky, not square raster cells. So that's really critical to doing the resampling. All right, so let's do a resample. Okay, so like I said, we're going to be resampling the larger cell down to a smaller cell size, which might be a little counterintuitive, but hopefully you get it. Okay, output cell size, we want to be the same as the ½ meter. So it's going to autofill that for me, but here's where it starts getting important to pay attention to defaults. Resampling technique. I've got a whole video on resampling techniques, and if you haven't seen that, you should watch it. I'll put a link down below in the comments. When we're working with continuous data, you have to use bilinear or cubic, and the difference between those two depends on your data. So make sure you're changing this to bilinear, and then here's the money shot. Get into the environments, and we're going to use the snap raster feature to make sure that our new output is aligning exactly with the other data set that we're going to be differencing it with. So when we're, of course, working with the 5 meter right now, so we want to make sure we're snapping the output cells to line up exactly with the ½ meter LiDAR. The rest of this I tend to leave, mostly because we've got everything we need here. For raster storage, this resampling method nearest is different than the resampling technique that we're using to run the tool. This is for storage. There's no reason why you couldn't change that to bilinear and bilinear. But anything you set here deliberately is going to overrule something that you've set here, but this is the trumping resampling technique that you need to set. This is the one that really matters. Okay, so again, I snapped the raster to the other data set, and then we're just going to run it. Okay, there's one more thing I forgot to show you in environments. It's really going to speed this up quite a bit. The processing extent. We can process that entire 5 meter data set down to a ½ meter, but imagine how much information that's going to be and how huge that file size is going to be. So this is a good opportunity we want to do an intersection of the inputs. That means it's only going to process the place where both data sets are aligning. And I think that's something that you will find will save you a whole bunch of time. So going back over here, yeah, everything looks good. Okay. Okay. My resample finished. I did run it using the extent of the smaller tile. The symbology is a little bit funky, and I think it might be drawing its symbology from the original data set. Let me see if I can turn that on here without blowing up my computer. So I'm going to go into the symbology, which you can't see, it's off your screen. Still pulling the statistics from the original data set. So I'm going to customize that and change it to match the statistics of my smaller data set. I'm just going to change it to 2600. It's close enough for our purposes. This is just symbology. Okay, so can you see what I'm getting at here? I think this is my new resample, and it had a min value of 1600, which is the minimum for that much larger tile. So I'm not really sure why it's doing that, and I don't have time to track it down right now. So I'm just going to remove this guy altogether. We've got our 2 data sets here. We've got the LiDAR and our resampled autocorrelated DEM. That's basically the 5 meter elevation data, but now we've just simplified it down to 50 centimeter. I like to go in and test what I've done, use the Explore tool to sample both of the data sets. So I'm going to use visible, they're both turned on, and click here and check my pop-up for values from each. So in that one location that I just sampled, the LiDAR is telling me the elevation is 2940, and from the autocorrelated it's only 2900, so we're about 40 meters off. If that doesn't sound like a sizable error to you for elevation data, then think again. So let's make a couple of quick hill shades so we can see the differences a little bit easier. I'm going to use the raster functions, which are in the analysis tab here. Raster functions, these are just temporary drawings. They're not, data sets that are going to sit in your files and clog things up. All right, so I'm just going to use this here. So here you can see the the hillshade type, they offer you traditional, which is what you get when you run the tool, or the multi-directional, which changes the lighting a little bit so you don't get the intense shadows. So let's do that. I'm going to do the LiDAR first. And then I'm going to run it again on the autocorrelated data, which is this one. And we'll do multi-directional as well, so we're comparing apples to apples. And I just noticed, what does this say? Ooh, off your screen, but hang on. It does give you the option to save it, which I didn't even realize. So you could use these raster functions as a shortcut to save your raster outputs, but I'm just going to create a temporary layer. Okay, here's why I think this is such a fun exercise. All right, what we're looking at is the resampled 5-meter autocorrelated data. Look at these pockets that kind of look like mercury, puddled mercury. And I'm going to use I think I'm going to use the swipe tool here. I've got my top layer selected, so when I swipe, I can pull this down and we can see the detail of the actual LiDAR below. And you can see areas. I'm going to zoom in a little bit. Okay, let's look at this kind of puddled area here. Look at the information right by my drop down. Look at that whole ridge line is being obscured. And it's kind of created this funky ridge line over here that doesn't really exist. So this whole, where I'm dragging the swipe tool, that whole ridge is gone. And this whole area really here is being obscured quite a bit. So we would expect to see a lot of error in these places. That's why we're going to do a DEM of difference. Now make sure you're not working with the hillshades when you difference these two data sets. You want to make sure that you're working with the actual elevation data. All right, let's get in and do that. Let's see here. It is we can use the Raster Calculator, or there's a tool called difference, or we've got sum, difference, multiply, divide, but this is my typical go-to. Okay, so this is where you're going to have to pay attention a little bit and figure out how you want to do it. But if I use the LiDAR as my truth, so that's this guy. I double-click to get it in there, and then I want to subtract the Monroe resample. Oops, I didn't get my subtract in there. Some tools, sometimes you have to double click and sometimes not. So what's going to happen is the places where the places where it's glossing over, the autocorrelated data is glossing over and kind of creating these artificially high surfaces, those are going to show up as negative numbers. So that might be counterintuitive. And because we know that the autocorrelated data is going to have higher values, maybe it makes sense to switch these around. And so we'll take our autocorrelated data and subtract our LiDAR. Monroe LiDAR half meter. Okay, and then for the output, let me just make sure I put this in the right spot. All right, let's run that. Okay, and when the tool's done running, this is our results here. So you can see these values are the difference in meters between the two data sets. It's showing us that because we subtracted the LiDAR from the autocorrelated data, that in some places the autocorrelated data is 65 meters, between 65 and 66 meters higher than the LiDAR, and in some cases the LiDAR is 12 to 13 meters higher than the autocorrelated data. This is something to be taken very seriously if you think you're going to use those autocorrelated DEMs for analysis because you think the resolution is better than the 10-meter data. Resolution, yes, but quality or accuracy, no. The 10-meter data is improved whenever LiDAR becomes available. All right, last but not least, let's use our awesome symbology techniques to put a divergent color ramp on this, and we'll drape it over a hillshade so we can really see what's going on. with that guy selected, I'm going to go over to here and pick a divergent color ramp. And then remember, we need to set the middle value to 0 so that we're, displaying things correctly. I don't know if you have a preference. I don't really care. I'm just jumping in here. And then let's customize this. And we'll set the min. I'm going to simplify and make it -115 and make the positive, 115. That'll include everything. Put 0 in the middle. And then I'm going to go up to the, come on, cooperate. Oh dear. Hold on one second. There we go. All right, I'm going to go up to my raster layer and blend this over the hillshade, which I need to find. I'm going to use the LiDAR hillshade as my base map. Okay, so then going back here. That's terrible. Let's try darkening it. It's a bit much. Maybe I'll change the transparency. That does a pretty good job. So these are areas. Wow, yeah, that's pretty striking. The red are areas where the LiDAR is doing a better job. It is above the, autocorrelated. Where the autocorrelated is displaying higher than the LiDAR is in green. And look at these two really dark pockets here are probably our pockets of the highest error. We can turn on our regular hillshade, or our other hillshade. Yes, you can see these are the pockets that are greatly being overestimated. And then here, these are the areas where the autocorrelated is underestimating the actual elevation. These were the other pockets that were being interpolated to a smooth surface, but the LiDAR was actually, that we were talking about how that ridge was just missing. And so that ridge got cut off, and it's losing all the elevation in these spots. Fascinating results. There you go. Have fun making a map with this data and conveying, what you're displaying for your audience.